I want to shortly introduce the particle motion with parametrics. So yesterday's focus was how to find the derivative. We talked about how to find the first derivative, how to find the second derivative, and how to use it for things like slope and tangent line. But now I want to get into more of particle motion, which is a very big push with parametrics. A lot of the questions are going to ask you things about how does something move based on its parametric equations. So I made a list of the 3 things that we can learn from the derivative in parametric mode, and then we'll talk about each one, how you find it and what you're looking for. So the 3 things we're looking for is how do we know when a particle is at rest? How do we know when a particle is moving left versus right? And then what is the speed of the particle at any given time? So I want to address each one of those individually. So first of all, at rest. So let's talk the derivative. So when we write the derivative parametrically, it's dy dt on top and dx dt on the bottom. To be at rest means that my velocity, which is represented by slope, has to equal 0. So this derivative has to equal 0. In order to get the derivative to equal to 0, the numerator of the derivative equation has to equal 0. So when they're asking us when is a particle at rest, what they're really saying is when does the y component's derivative equal 0? So we're able to derive that individually. It's a lot simpler than doing the entire derivative and set that equal to 0, often involving basic factoring and solving. For the right versus left motion, that's going to focus entirely on the x component because we think of x as our horizontal component. So dx dt is the key to figuring out if it's moving to the right or to the left. As you would probably expect, if dx dt is positive, then we say the particle is moving to the right. And if dx dt is negative, then it's moving to the left. This really reiterates what we did in chapter 7 with regular equations and motion. And then finally, speed. And you're going to notice speed. I put the whole equation on here. It uses both parts of the derivative, the dx dt and the dy dt. And both of those things are under a square root and being squared. So what you'll have happen is it's basically like a big Pythagorean theorem kind of question. It's kind of where it comes from if you had to prove it. So you're going to take your dx dt derivative, your dx dt value, square it, take your dy dt, square it, add those values together, and then take the square root of it. You will always get a positive value, which should make sense because speed, unlike velocity, speed doesn't have a sign. Speed is always positive. So no matter what I put in there, no matter what my equations are, when I square them and then square root them, I'm always going to get a positive. So I'm going to do just one question with you that kind of takes you through a little bit of everything that I just talked about. So you have to be given your x equation and your y equation. So we're going to do x to be 2t squared minus 3 and y to be 1/3 t cubed minus t squared minus 15t plus 3. So we have a big equation for y, a little smaller equation for x. So first we're going to talk about at rest. So the question will ask exactly that. When is this particle at rest? So we're going to take our y derivative. We're going to take dy dt, which is a pretty easy derivative, just power rules, power up front, power 1 last. I get t squared minus 2t minus 15. Set that equal to 0. If they don't let you use a calculator, then it'll be factorable. If they do let you use a calculator, then they can get pretty ugly. So it factors t plus 5, t plus 3. So we have 2 t values, 5 and negative 3. Now, when you're dealing with particle motion, now we are really looking at t as representative of time. We cannot have negative time. We cannot go back in time. So unlike the ones that we did yesterday that were all based on a coordinate plane and slope, where we were working with positive and negative t's, that is not the case with motion. We can only have positive, so t equals 5 would be the only time that it is at rest, meaning not moving. Now I want to look at right versus left. So often what they'll do is they'll give a specific time and ask at that time, what's it doing? So I'm going to ask about t equals 3, what's the movement? So right or left. So we're going to look at the x derivative, dx dt, which is 4t. We're going to put 3 in for t, so 4 times 3. We get a positive value, so we say that it is moving right. When they say justify or explain, you can truly just say my derivative value is bigger than 0 or my derivative is positive. You don't have to get super detailed beyond that. And then the last thing they can be asking you is about speed. So they have to give you a time. So let's say they want to know the speed at time equals 1. It has to be a positive time. Again, we're working with time. So we're going to take both the x and the y derivative, which actually we've already done. So here's my x derivative. Here's my y derivative. We're going to go under the square root. and put the x derivative, quantity squared, plus the y derivative, which is a little bit longer, quantity squared. If you've already found dx dt and dy dt and you just want to write generically dx dt squared plus dy dt squared and then do the work behind the scenes, that is fine. You basically just have to show your knowledge of how this actually works. At that point, you can put 1 in. So when I put 1 in, I get the square root of 4 times 1 squared. So the square root of 4 squared is 16 plus 1 minus 2 minus 15 is negative 16 squared, which is 256. So I have the square root of 16 plus 256, which is the square root of 272, which if you're not allowed to use a calculator, you are perfectly fine leaving it in that form. If you are allowed to use a calculator, just make sure you go 3 decimal places. It is 16.492. And they do not expect units because they don't tend to give units. So as long as you just have that value either as a radical or as a decimal, you are correct. So that's one example covering all 3 questions that will be asked. At rest, meaning derivative is 0, dy dt is 0. Right or left movement, looking at the x component and seeing if it's positive or negative, and then the speed formula that you do need to know and be able to reference.